Okay, so we continue our discussion from last time. So last time we introduced the Ito integral, in particular the Ito integral for simple processes. For doing that, we have introduced a special class of functions, which is the M2 class, and we have defined the Ito integral for this special type of functions that are in the M2 class that we call simple processes. That is to say, all those functions that can be represented as simple sums of random variables. We have seen some of the basic properties of the integral related to simple processes, and what we do today is to continue building the full integral that will be the object we will use later on, possibly already at the end of this class, if not starting from next week. And from next week, we will enter finally, into the financial treatment of these quantities. Now, what we have seen is that if I introduce the Ito integral for a simple process, it has a lot of nice properties. So for sure, I can take the integral of the sum as the sum of the integrals, which is useful. I can multiply by a constant, either the integral or the function, and then essentially it's the same stuff because I can always move the constant in and out of the integral. I have a very important property, which is the fact that the expectation of an Ito integral is always equal to 0 for the simple process. But we will see later today that it's true in general. And we also had the so-called Ito isometry, which is extremely important when we are interested in computing, for example, the second moment of an Ito integral, but is also beautiful and useful from another point of view because it allows us to move from the Ito integral to a standard integral we can play with. So it's the famous movement from dB squared to dt. Now, another interesting property of this integral that it is inherited in general for every Ito integral is the fact that it defines a martingale. It defines a martingale, obviously, with respect to a specific probability measure and a specific filtration. Because remember that a process can be a martingale under a given probability measure, but not under another. Or it can be martingale with respect to a filtration, but not with respect to another. You will see that a great part of what we do in this course is actually to find the right filtration and the right measure such that the discounted value process or the discounted price process of an asset is actually a martingale. We will define the risk-neutral measure actually as the measure such that the discounted price process is a martingale. And why we do that? Because we can prove, and I will show you that, for example, under the physical measure, it's not guaranteed that the discounted price process is a martingale. So we change the measure in order to have this nice property, which is also in line with some of the assumptions that we have made so far. So in the M2 class, one of the assumptions for us was the non-anticipating nature of the quantities we are playing with. That, if you want, bridges in a sense, also to martingality. Okay, another property of the Ito integral for simple processes is the fact that it is martingale. So we can show that if we consider the Ito integral 0 small t, where small t is obviously in 0 capital T, of phi r omega d b r omega, and in a minute, as I told you last time, I will drop the r and the omega because it's somehow evident. So if we consider this object here, this object is a martingale, so let's call this object q of t, okay? So if I consider q of t, so this Ito integral from 0 to time t, this object here is a martingale with respect to with respect to P, which is our probability measure on the space omega Fp, okay? And the filtration Ft, for T and 0, capital T, where Ft is what, as last time, is a natural filtration generated by the Brownian motion, okay? We will see that later it can be maybe something else, but for the moment is the natural filtration generated by the Brownian motion. Now, in order to prove that our integral here is a martingale, we have to check a certain number of properties. Now, the first thing is, for example, the measurability part. I hope you agree with me that the quantity Qt is Ft measurable. We can take that as evident. As you will see in this course, sometimes I like to be a little bit more rigorous. Sometimes it is when we can be a little bit quicker, because otherwise we can stay an entire semester on these kind of things. So one thing is that Qt is Ft measurable. Why? We are assuming phi is a simple process, so it means that it is in the M2 class, okay? Even if I don't tell that, we are always playing with quantities that are in the M2 class. So it's in the M2 class, so we have that it needs to satisfy this thing, and the Brownian motion is by definition adapt to its natural filtration. Every stochastic process is always adapt to its own natural filtration, so to the filtration that it generates. Okay, so the fact that we have this measurability is somehow satisfied. Now, another thing that we have to verify is the integrability. Now, for what concerns the integrability of our quantity, what we want to show is that we can take the expectation of Qt, and we want this quantity to be finite. Why? Here you can give different interpretations. What I like is the trivial one. You are defined a process, a martingale, that relies on the expectation, okay? And you want the conditional expectation to behave in a certain way. So you want the expectation to be finite, to be defined. Okay, so we take this, and remember that if the expectation of a random quantity is not finite, then also conditioning does not help. So if we want to consider this guy here, it's like taking the expectation of what? Of the integral, 0 t phi r omega dB r omega. But now I hope you will agree with me that this quantity is smaller than equal to the expectation of 0 t phi dB squared, and then I take the square root. And now here we can exploit the fact that we are playing with a simple process. And in particular here, we can use the Ito isometry. Okay, so if we do that, we know that this is equal to the expectation of what? Of 0 t phi squared dt. Everything under the square root. Okay, so I'm substituting the expectation of the integral squared to what is the expectation of the integral of phi squared dt. That's the Ito isometry. But now, what do we know about phi? Phi is in the M2 class. So what's the third requirement of a function to be in the M2 class? That this guy is finite. Okay, so this is finite. So the integrability part is given. So let me write that here. This is finite. Now, what we need to prove is the actual martingality property. So the fact that we have the martingale. Now, take our usual partition, okay? And just add a small detail. So we know that our partition is such that T0 is equal to 0, smaller than T1, smaller than a certain number of things, smaller than a quantity Tn that we set equal to time S, smaller than Tn plus 1, smaller than, let's introduce another quantity. I have n, I have m, I have a tq, which is equal to small t, smaller than our final Tn, which is equal to capital T, okay? Or if you want, you can simplify everything by setting directly Tn equal to T. This is just to be pedantic, okay? But you can work on the proof in the same way. Okay, but just to be consistent with the notation we had so far, Tn is equal to capital T. Now, what we want to do is to compute this quantity. We want to take Qt. We want to condition on f of s, where s is smaller than t, okay? And obviously both are in the interval 0, capital T. We want to compute this quantity, and what do we want to prove? We want to prove that if I take Qt and a condition on the sigma algebra Fs, so that we stop our filtration at time S, that is to say, imagine that this represents the price of an asset, and we want to evaluate the expected price or the expected return. We will see that it's always nicer to play with returns in terms of predictability because they tend to be stationary, while prices are not necessarily, most of the time they are not stationary. So if you condition a time S, it means that you want to use the information that we have up to time S, okay? So it means that if we want to price the return of an asset, if we want to price the price of an asset, what I want to do today is to exploit the information I have so far, because I cannot assume, and I don't want to assume, that I need information from the future, because otherwise, I mean, unless you are a fortune teller, there is nothing that you can do. Okay, so we want to prove that this quantity is actually QS. Okay, now this quantity is equal to what? Is equal to the expectation of this guy here. Okay, so 0 t phi r omega d b r omega. Condition at time fs. At information at time s, sorry. So condition on fs. Now, what can I do? I can substitute, this is a simple process, okay? So I can substitute the definition of the integral for the simple process. So this is equal to the expectation of what? I can take the sum for j from 0 to, I have to stop in t, so it means that I have to stop at time tq for me, okay? So from 0 to q, okay? Of what? Of a j omega, if we use the representation we have used last time, that multiplies where aj is a random variable, that multiplies what? The increment of the Brownian motion in tj plus 1 omega minus btj omega. And everything, conditioned on fs. Now, I hope you agree with me that I can split this sum here into two parts. I can sum from 0 up to time tm, that corresponds to s, and I can then sum from Tn plus 1 up to Tq, which correspond to T. Okay? So I can write this as the sum of j from 0 to n minus 1 of what? Of a j omega b t j plus 1 minus btj plus 1, I remove the omega, minus btj. Okay, that's the first part. Plus the sum, and here we take k that goes from m up to q minus 1 of what? Of a k omega, and here the increment of b t k plus 1 minus b t k. And everything conditioned on f of s that, if you want, is equal to f of Tm. Okay? Because we are taking Tm to be equal to s. Okay, now one thing that we know is that the expectation is a linear operator. Okay, so the expectation of the sum is the sum of the expectations. And this is also true for the conditional expectation. So if you want, I can split this guy here into the expectation of these plus the expectation of these. Both terms conditioned on Ftm or Fs. They are exactly the same stuff. Okay, let's see what happens if we do that. I start by considering the first part here, okay? Just this first part here. So this is the expected value of what? I just copy the sum for j from 0 to m minus 1 of a j omega, and then the increment of the Brownian motion, btj plus 1 minus btj. And everything here is conditioned on Tm. But what happens here? This is time Tm, this is time s, and these quantity are up to time s. Okay, so for measurability, what can I do? For measurability, I can just do this. It's absurd. Okay, so this is, let's call this A. Now let's consider B. Okay, A is this guy. Let's consider B. If we consider B, this is the expected value of what? Of this sum. Okay? Nice. Okay, this is the expected value of this sum. That is to say, the sum for k from n to q minus 1 of a j omega, ak, sorry, ak omega, and then the increment of the Brownian motion, tk plus 1 minus btk. Everything conditioned on Ftn. Okay, but now here, what do we have? We can exactly apply the same reasoning that we had in the first lesson in terms of measurability. First of all, I can take the expectation within the sum. Okay, so I can take the sum. This is a finite sum. I can take my sum of the expectations. So it means that I can transform these, if you want, into these. And now this is the expectation of a product. But again, for measurability, I can split thanks to measurability, I can split the expectation of the product into the product of two expectations. One expectation is the expectation here, so the expectation of the A, K, omega term. And one expectation is the expectation of the increment of the Brownian motion. And both expectations will be with respect to the filtration. Okay. So, my bad. Okay, for what concerns these, do you agree with me that I can ignore the conditioning because of the measurability property of the random variable A? Okay, so we know that because of the properties of phi. For the second part, what do we have? We still have the conditioning, so btj plus 1 minus btj. But now, what is this guy here? This is a future increment of the Brownian motion with respect to time Tm. Okay? Because this is in the future. Remember that our k is from m on. Okay? So if I take these, k plus 1, like m plus 1 minus m, is in the future. So it means that because of the property of the Brownian motion, the future increments are independent from the filtration. And it means that I can also get rid of the conditioning for what respect the filtration. But then this is what? This is the expectation of the increment of a Brownian motion. So I don't care about what this guy is. I have this guy here, and this expectation is 0, because it's the increment of a Brownian motion. So this guy is 0. It means that this term here disappears. But now consider this. Remember what we have chosen with respect to Tm equal to S, and you will see that this is equal to the integral between 0 and S of phi dB. Okay? Which is Qs then. So we have that actually our Brownian motion allows us to build this nice Ito integral for the simple processes, and we have that this Ito integral is a martingale with respect to P, which is the probability measure that governs the Brownian motion, and with respect to the natural filtration generated by the Brownian motion. Okay, so this is what we have in terms of martingality. So we know that it is actually a martingale. Now, what we want to do is to develop, to introduce the general integral. We want to introduce the general integral for a generic f in the M2 class. In order to do that, we have to introduce the concept of approximating sequence. Because as I told you last time, in reality, when we play with a generic f, we will see that the Ito integral of this f can be seen as the limit of a sequence of Ito integrals for simple processes. Okay, so what we have to find is the proper sequence that satisfies this. Okay, always need a shower after that. A proper sequence that satisfies our construction. Now, the concept is that of approximating sequence. So we introduce definition. Let f be a function in the M2 0t class, a sequence phi n in M2, And since we are using the standard notation, is a sequence of simple processes in M2. A sequence of simple processes in M2 is said to be an approximating sequence for F if we have the following relation. So the limit for n tending to infinity of the expectation of what? Of the integral between 0 and capital T of f t omega minus q and t omega squared dt, yes, is equal to 0. So we require this condition. If the sequence phi n is such that this limiting condition on the expectation holds, we say that the sequence of simple processes phi n is an approximating sequence for our function f, which is still in M2. Okay? Now, this is a very important object. So this approximating sequence is a very important object that has a certain number of properties. We will just consider the few ones that we need for the rest of the course and for building our integral, but it has a lot of nice properties that it inherits from the fact that these are simple processes. So that if I have a sequence of simple processes, I can define a sequence of integrals on simple processes with all the nice properties that we have seen. Now, we have this theorem, which is important. For f belonging to the M2 class, let phi n be an approximating sequence. It means that it satisfies this. Okay? Fine. Then the sequence of integrals phi n dB converges in quadratic mean. So I have my sequence that approximates f, simple processes that approximate a generic f in my M2 class. Then I define the sequence of the Ito integrals for simple processes based on my sequence phi n. And what I can show is that it converges in quadratic mean. Okay? This is very important because knowing that it converges in quadratic mean then automatically implies the convergence in other types of properties for what concerns the moments, but not only. And these are things that we will exploit. Okay, so let's try to prove these. How can we do that? I can take two elements of my sequence phi n. Okay? So take two elements, phi L and phi m of the sequence, okay? And assume that they are L and m are different, obviously. So we take phi L and phi m to be two different elements of our sequence. Now, what can we do? Let's consider this quantity. I take the expectation of what? Of the integral between 0 and t of phi L dB minus the integral 0 and t of phi m dB. Why? Because at the end of the day, what I can show, if I want to prove this theorem, what I can show is that it represents a Cauchy sequence in quadratic mean. Okay, so if I prove that, essentially I have my theorem. So let's take two different elements of my sequence and let's define the expectation of what? Of the integral of phi L dB minus the integral of phi m dB. Now, using the properties of the Ito integral, I can immediately shrink the two integrals into just one integral. Okay, so I can just take the integral between 0 and t of phi L minus phi of m dB, everything squared. But phi L and phi m are elements of the sequence phi n, so it means that they are simple processes. If I take the sum of two simple processes, I get a simple process. If I take the difference of two simple processes, I get a simple process. Okay, it's very simple to show that. Just recall that every single process is just a sum of random variables on intervals that we acknowledge with indicators. Okay, so if I take then the sum or the difference of these quantities, you still have the sum of random variables on intervals. So it's a simple process. But if this is the case, what can I do? I can immediately apply the Ito isometry to this. Okay, so it means that this is equal to the expectation of what? Of the integral 0 capital T of phi L minus phi m squared dt. Okay? Because this is a simple process, so I can apply the Ito isometry. So I just take the argument squared, and dB becomes dt. Okay. But this is equal to the expectation of what? Of 0 capital T phi L minus f plus f, I can add and remove f, minus phi m squared dt. But if this is the case, then what we know is that this quantity here is smaller than equal to what? The expectation of 0 t, 2 times, because it's the, I'm squaring, phi L minus f squared dt, plus the integral 0 t of phi, f minus f m squared dt. But for L and M tending to infinity, what do I know? Now I have the expectation of this, ignore the two. So I have the expectation of this thing, so I can take the expectation inside. Okay? So that will come the sum of the expectations. But what do I know about phi L and phi M? Phi L and phi M are simple processes, fine, but they are part of an approximating sequence. So they satisfy this. So for L and M tending to infinity, it means that this guy here tends to 0, and this guy here tends to 0. So everything tends to 0. And so we have our convergence in quadratic mean. The trick is to exploit first the isometry, and then the definition of approximating sequence. So this convergence is extremely, extremely important, because you will see in a minute, when we introduce the general Ito integral, this is the basic trick that you exploit every time. Every time you want to prove that the expectation of the Ito integral is equal to 0, and I'm speaking about the general integral, is equal to 0, you use this. If you want to prove the Ito isometry for the general integral, you use this. If you want to show the martingality, you end up using these. Also, together with other tools, but you always need these at a certain point to prove your result. Okay, we can then give another important result, which is essentially the starting point of everything. In the lecture note is theorem 2, and it's extremely, extremely important. Now, proving this theorem is not, or to be exact, it can be extremely complicated, or it can be relatively simple. Obviously, it depends on the level of sophistication that you want to use. But that will be true for many results that we see together. For example, we will see a very important theorem, which is called the Gilsanov theorem, that is fundamental in financial mathematics and in mathematical finance. Without that, we can just close down and stop blabbering about these things. But the Gilsanov theorem can be given at different levels. We will just cover what we need, because it's totally useless to cover the most general situation that takes 2 days to be proven, and then we will never use it. Okay? So also here we take what we need. If you are interested in knowing all the small details, but according to me, this is already at the PhD level, possibly, there are beautiful books. So a very nice book, it's the Karatsas Shreve. There you find everything. So there you can really find whatever you want in terms of complication. By the way, I forgot. This is the theorem that we have just seen about the convergence in quadratic mean is important, and it also has an immediate corollary. It means that if instead of considering the sequence phi n, I consider the sequence phi n and another sequence beta n, and they are both approximating sequences for the same f in M2, then it means that the two limits of these sequences exist, and the two limits coincide. Okay? So you can start with whatever sequence you want. You will end up with the same final integral. So that's a nice result. Theorem. This is called the Ito approximation. And it's extremely important. And it says the following. For every f in M2, there exists a sequence h n of elements of M2 such that Hn is an approximating sequence sequence for f. So if I have an f in my M2 class, I will always be able to find an approximating sequence of functions in M2. Now, there are different ways in which you can prove this. I can already tell you that the functions that you can use here are of different types. In a sense, the paradox, I can tell you that you can always find a sequence of simple processes. So if you want, the sequence Hn can be just a sequence of simple processes. But the fact is that if you want to prove that this sequence is a sequence of simple processes, and this is the case, the proof is longer and more tedious than if you split into different types of functions, which is what we do. What do I mean? Instead of proving immediately that this sequence is a sequence of simple processes, I will show you that if so we will use three lemmas. The first lemma tells us that if G is a bounded and continuous function in M2, there exists a sequence of simple processes that approximates G. And these are simple processes. So to prove that this sequence is made of simple processes, when we start from a function G in M2, which is bounded and continuous, it's simple. The second lemma tells me that if H in M2 is bounded, then there exists a sequence of functions Gn that are bounded and continuous that approximate H. That approximate H. And you can guess, I hope, the third lemma. The third lemma tells us if f in M2 is a generic function, then it can be approximated by a sequence of functions H that are bounded. So the trick is, and since the simple processes obviously are here, and this guy approximate these, and this guy approximate this, at the end, it's, if you want, a sequence of simple processes. But you can split that in three parts, and this trick is actually very common in probability. You might recall from other results that you have seen. So you have a generic function. First, you consider the simplest case in which the function is bounded and continuous, and you approximate that easily with simple processes. Then you say, okay, I remove the continuous, I just consider bounded, and then you can show that you can use a sequence of bounded and continuous. And then you say, okay, I remove everything, it's just a generic function that satisfies the requirements of M2. That's fundamental. And then I can use just a sequence of functions H that are bounded. Okay, we continue after the break.